Okay, so on number 4, page 46, we're analyzing h to see if it's proportionality of x and y, proportionality of changes of x to changes in y. Changes in the quantities. So what would?
Because in the quantities we have 2 to 3 inches. 2 to 5, which is 3, right?
So you're saying that and that. Okay.
So
What about the second one?
we have negatives in there, so I don't see it.
Any changes? We can have changes. Changes being proportional with negatives. Oops. Are you finding one of those tables that has changes that are proportional?
Yes, sir.
You found one?
Right,
Table
table 2.
2. Someone else find that the changes are proportional in table 2? Let's look at that one. So in table 2, in order to check the proportionality of changes, we're going to have to look at some changes. So we could look at the change from x from 1.3 to negative 4. What change is that? From 1.3 to negative 4 is how much of a change? Negative 5.3, right? So that's the change from here to here. So what's the corresponding change then in y? So that negative 5.3 comes from negative 4 minus 1.3. So the corresponding change in y would be 14.4 minus 12.015. What's that? Let's look at another change in x. The change in x, say, from 1.3 to 9.7. How much of a change is that? 8.4. What's the corresponding change in y when x changes from 1.3 to 9.7?
Negative 3.78.
He says negative 3.78. Just confirm it. I agree. Do you see what I'm doing? Okay, so how can we see if, just from those two examples, if we have changes in y proportional to changes in x? What can we do now? How do we test it? How do we test that these two quantities are proportional? Scaling factor, okay? Okay, or what's another way? So scaling factor could work, but we want to do it a different way. Yeah, constant multiple, which would be have to be a number that we'd multiply this one by to get this one. So is there this constant multiple? We'll call it k. And how would you find it? That's right. Did you get negative 0.45? Do you also get negative 0.45 when you take negative 3.78 divided by 8.4? You also get that? Same thing?
Yes.
Okay. So, and we got one more x change that we could test. We could test from negative 4 to 9.7, and then the 14.4 to 8.235, and we should get the same. Okay, so what are we saying? We're saying that delta y over delta x is always this value, negative 0.45. So what do we have?
Slope.
What's that?
Slope.
Okay, we have the slope of the graph. What else do we have?
Rate of change.
What kind of rate of change?
Constant.
That's what we talked about Friday. So if the changes are proportional, if you always have delta y the same relative size to delta x, in this case negative 0.45, then you have constant rate of change. And we have the slope of the graph. So remember, this is slope. This is the constant rate of change. This is the relative size of delta y to delta x, because we have proportionality of the changes. All right, so let's see how good a graph I can draw with this thing. All right, so let me undo that, sorry. Graph like this. So what's the first x and y point? Negative 2, 13.6. Okay? Next point is Oh no, wrong. I'm looking at the wrong one.
And 1.3.
Sorry. What is it? 1.3 and 12.015. So here's 1, 2. 1.3, 12.015. Next point, -4 and 14.4. And then finally 9.7 and 8.235. Okay, so those are the 3 points they gave us. If the changes are proportional, like we have here, then what can we say about those 3 points? Linear, okay? So proportionality of the changes implies that the graph will be linear. Okay? And if I start here, and if I go over some amount, call it delta x, how much will delta y change over that delta x? Well, how much? Will it change -0.45, the amount of y? Will the change be -0.45?
No.
What will it be?
Negative 0.45 times the change.
Yeah, so remember it's relative size. The relative size of change in y is always -0.45 of the change in x. That's what that number -0.45 means. It means the relative size of the change in y given the change of x. So x changes this much, y will change by -0.45 of that. Or -0.45 times delta x. What if delta x changes this much? Then how much will y change? -0.45 of whatever the change in delta x is. So that's the proportionality of changes, and then the result is what kind of graph? A linear graph, okay? And when you remember linear graphs from your past, you remember a formula. What was the formula? Y equals mx plus b. Okay, and so look at this. So this is the relative change of y with respect to x. So to get the change in y, we're going to go that much delta x. And we know that that's our slope, right? That relative change. Or the slope of the line is our delta y over delta x. How much y changes relative to the change in x. So what is b? Okay, it's the y-intercept. So it's what you would get if x was 0. So if you plug 0 in here, then that would be what you would get for y if it was 0. Okay, so for this, for this particular problem, so the y-intercept is right here, can you use the idea of constant rate of change and our as relative change to figure out what is b? What does b equal? Take a minute, see if you can get it. What does b equal? So don't try to remember something that you did in the past, like a sudden procedure. Can we use what we're talking about here, proportionality of the changes, to get what that y value is where it crosses the y-axis? Okay? So that we want to really practice our understanding of constant rate of change to find b. See if you can do it. Go. Here's a hint. Start at this point right here. Use this point right here. Start at that point to do it. Is that what you did?
Yeah.
Yep. So start at that point right there and use this idea of constant rate of change to find that y value, this b.
Give me this number added to what you, what y was before, the other thing was what it was, what it is now.
Need some more space. It's going to take a while.
Do you have different eraser sizes?
Yeah, I could, well, this is actually just a white pen. I just made it, so I could even make it bigger, yeah. Okay, that's good. So, anyone think they can do this? I know you can do it. Anyone think they got it? So how can we use the constant rate of change? What did you do first?
I put 12.05 into 5, or sorry, 12.05 equals,
Okay, so you plugged it in here?
yeah,
Okay, and then you plugged x in here,
yeah,
and then solve for b? Okay, so that's a totally valid way to do it. But that's fine. But can we do it using the idea of constant rate of change? See what I'm getting at? So can we think through a process that utilizes this constant rate of change? Yeah, that works. That works.
So in order to get to 0 from 1.3, you have to subtract 1.3, which
Okay?
is your change in x,
So my change in x from this point to the point I want is,
negative 1.3.
he wants negative 1.3. Okay?
And then to get your change in y, you then have to multiply by negative 0.45.
Nice. So the corresponding change in y would be negative 0.45 times, that's supposed to be times, negative 1.3.
Which then gives you 5.85, I believe. No, 0.585.
0.585?
Excuse me. And then you add 0.585 to your original point, which is 12.015.
Okay, so zooming in on what he did there, he said this is going to be negative 1.3. And so I know that my change in y is always going to be negative 0.45 of that. So that corresponding change in y will be 0.585.
Correct.
And so now I need that y value. So this was the change in y. How am I going to get that y value right there if we went through a change of 0.585? Add it to the y we had before. So b is going to be the y we started at. Plus how much we changed when we went through the delta x. And what does it equal? 12.6 exactly.
Yeah.
Okay, so in this case, so what's our equation of our line then? Y equals negative 0.45 x plus 12.6. Anybody have a question on that? So some of the homework problems, they really force you, the way they've set it up, what they've given you and what they're asking for, they're really forcing you to use this kind of reasoning. That if you make it delta x, you're going to then multiply it by your proportionality constant, which tells you the corresponding change in y. And then if you need to add it to an original y or whatever you need to do. So they could ask it in many ways, different kinds of problems. But if you understand this idea of what that number negative 0.45 means, and you know how graphs work, just y and x coordinate, then you should be able to work your way around any problem. That's the idea. Questions on this example? Okay, so we're going to So in summary, when you have proportionality of changes, you have constant rate of change, and the graph will be linear. Do you necessarily have proportionality of the quantities then? Like in this one, do we have proportionality of the quantities?
No.
Definitely not, okay? The original quantities are not proportional. But if the changes are proportional, you get a linear graph and constant rate of change. Key idea of calculus is constant rate of change, really important. Okay, so let's go on to page 49. We're going to go on to worksheet 5. Numbers 1 through 5. Just like it, I'm not going to change anything. This is a great worksheet for introducing this new topic. We're going to look at average speed. So 1 through 5, which takes you on to page 50. I'm going to come around and check as you go. All right, so I may say, wait, you got to go back and do something else. Or if you want to catch me and ask a question, work together. See if you can make, in about 10 or 15 minutes, if you can make it through 1 through 5. Okay? don't. What distance does it travel? Move from mile marker 363 to 373. So
So that's 10. But if you took your car 30 minutes to travel from Topeka to mile marker 373 and 2 minutes to travel, you can know the distance from here to here.
distance from where to where?
From Topeka to the mile marker 363.
You don't need to know it. How are you going to find the constant speed? I mean, what's your approach here? I mean, what are you thinking? What are you thinking you're going to do to find the constant speed? How are you thinking about this? You need to know what
Yeah, you don't know the speed.
relative distance in units of time, right? So it's just like delta y is delta x. So what will delta y be?
The distance,
Change in distance. What will delta x be?
change in time.
That's what you need.
Okay. I don't think so. I got it. Makes sense. Huh? Yes. I know it's last 2 nights trying to bed with the stuffiest nose ever. It's ridiculous. Don't know where it's coming from.
That makes so much sense.
Does it? What I did?
I think that
I was reading it wrong. I have this right, he's speeding. So, I don't know about right. Never mind.
Do I have that right?
Yes.
Okay, so this is for, is that C? So here's kind of an illustration to help me with part C. So Topeka, so like above the line is our minutes of Topeka. Below the line is kind of like a distance. It's not, we don't know if it's distance or not, but we just know that when you hit 18 minutes, you're at mile marker 363. 30 minutes after Topeka, you're at mile marker 373. Okay, so if we want to find at what constant speed in miles per hour, then we're asking what is delta y, what is delta x, what is k? Remember this? So reading the information and trying to organize it and to summarize it with the symbols, right? So we can be concise about it. So what is delta y in this case? Distance, be more specific. What? So what?
Oh, sorry. Distance traveled from marker 363.
Change in distance from marker 363 to 373. What is that? Nice and easy. 10 miles. Okay. What's the change? What is x in this case represented by? So what is it representing? Delta x is going to be the change in time. Is it 12? So, what is K? It's our constant rate of change, or the relative size of distance in the units of, or relative to time. Relative size of distance to time. And what's that number? Point what? Point 8333? Okay, so what is that? That's miles per so if we go 0.833 miles every minute, how will we find how many we go every hour? Every minute, 0.833, 0.833, 0.833. So in an hour, 60 of those, right? $50 miles per hour. Okay, when you get to the graph now, be very careful. What is the distance quantity you're graphing? Which distance is it? Remember, we can find 5 different distance quantities that we could identify and define in this situation. So specifically, what distance quantity are you graphing? Miles traveled from what point? Mile marker. Is our distance the miles from 363 to 373? Is that our distance variable? No, because that's that's a constant quantity. That's 10 miles. So we want a varying quantity of distance. So we want the distance in miles since we passed marker 363. So what will that quantity be when we get to mile marker 365? What will D equal? When we get to mile marker 365, will D equal 365?
Yeah. No, D will equal 2.
D will equal 2. Do you see? It's distance from mile marker 363. And what about the time? So when we reach mile marker 365, okay? So when we reach mile marker 363, at mile marker 363, what is the time equal to? 0. It's not equal to 18. Do you see? So you got to be very careful the way they've defined those variables. Distance from 363, time since you passed 363. Okay, make the graph. Go for it. Sorry, this is per hour. Finish. Okay, I see lots of people. We want, remember we said delta y was change in distance and delta x is change in time. So your x-axis is going to be time. What time? Time elapsed since passing 363. So we want time elapsed since passing 363, and then our y quantity is? Distance in miles past 363. Okay, so this is what you're saying here is right there. 362 miles from the top mark of 363. time in t?
Switchies.
Add up.
Go back to 63. 2 minutes later, the value is t. Time since passing 363. Starting at 5, half a mile per hour, 363. Distance from we get to number 365. The work value of d. 2. Not 365. We'll go consistent with this for For instance, when you get to mile marker 365, which is
Yep.
the distance from 365. So we're going to do the distance from
Trick.
365.
Don't judge. It's fine. I'm jealous.
Distance from the 365. All right, just use an example. So if we want the distance from the 363 mile marker, well, when you get to mile marker 367, then what is the value of d? What is this? So 363, so now we're going to get to 367. 363 and 367. This value of d is 4, because that's the distance from mile marker. Here's the key in this, defining these distances. The distance is since you pass 363. So when you get to mile marker 367, what is the value of that variable d? when you get to 367? It's 4. So you should have 4 here and not 367. Because what are these values? These values are the distance from mile marker 363. How far you are from 363. So here, at what mile marker are we now? If d equals 8, at what mile marker are we at?
371.
363 plus 8. So we're at mile marker 371 when d equals 8. So that's what you want, starting at 0 miles from 363. Similarly, time. 2 minutes isn't 2 minutes plus the 18 minutes that took us from Topeka. So this says no, Topeka's out of the question now. Okay, so let's just quickly. What I want you to so let's see. We didn't have time to get to the big point here. So if the truck passed you at 363 and then you passed the truck at 373, then what was the distance of the truck compared to your distance in those 10 miles? The truck passed you at 363 and then we passed the truck at 373. The truck passed us at 363, and then we passed the truck at 373. The truck is always covering more distance than us for those 10, 12 minutes or 10 miles, right? And then we passed the truck again. How many miles did the truck cover in those 12 minutes? So the truck, it covered how many? 10 miles in 12 minutes. What is that speed? Isn't that still the same 50 miles per hour? The car, we went on cruise control 50 miles per hour. Was the truck going 50 miles per hour the whole time? No. Okay, it was going faster and slower, okay? But the car at cruise control, that constant speed represents the average speed of the truck. So what is average speed? It's the constant speed to go the same distance in the same time. So the constant speed of the car represents the average speed of the truck. The truck had some average speed over those 12 minutes. That's represented by the car at cruise control, 50 miles per hour. Okay, you got homework due Wednesday.